Welcome to the Nerdjacker's Vault. Today we are reading The Optics by Greek geometer Euclid, translated by Harry Edwin Burton and Syed Mahdi Hassan. Translator's note: this is a working translation of Euclid's Optics. The original text and the translation by Harry Edwin Burton is written in a highly technical, proposition-by-proposition style with dense proofs that can be difficult to follow when read aloud. In this version, the core ideas, major results, and logical flow are preserved, while the language is adapted for clarity and natural listening. Repetitive steps are streamlined where they do not add new understanding, and geometric constructions are described in words to maintain accessibility. The mathematical rigor and Euclid's remarkable insights remain intact. This is not a literal word-for-word rendering, nor a modern commentary, but a translation intended to let the beauty and power of the original ideas reach a broader audience. First, we need to set some definitions. 1. Let it be assumed that lines drawn directly from the eye pass through a space of great extent. Imagine your eye at a single point, and from it, straight lines extending outward in every direction. These lines travel through the space in front of you, reaching far beyond what you immediately notice. You don't see the lines themselves, but you can think of them as forming a kind of path between your eye and whatever you are looking at. Anything you see lies somewhere along these lines, as they pass outward into a wide and open space. 2. The form of the space included within our vision is a cone, with its apex in the eye and its base at the limits of our vision. Imagine all those lines leaving your eye, spreading outward into the space in front of you. They don't go in a single direction. They open up wider and wider, forming a shape, narrow at your eye and expanding as they move away. If you gather all those lines together, they form something like a cone. Your eye at the tip, and everything you can see lying across the wide opening. So your vision is not just a point looking out, it's a shape extending into space, with everything visible contained within it. 3. The things upon which the vision falls are seen, and that those things upon which the vision does not fall are not seen. Think again of those lines spreading out from your eye. Only the things that lie along those lines are seen. If an object falls within that spread, within that cone, it becomes visible to you. But anything outside of it, even if it is close by, remains unseen. So seeing is not just about what exists, but about what your vision actually reaches. 4. The things seen within a larger angle appear larger, and those seen within a smaller angle appear smaller, and those seen within equal angles appear to be of the same size. Imagine looking at two objects, one close to you and one farther away. Even if they are the same size, the closer one seems larger. That's because the lines from your eye spread out more to cover it. The farther one takes up a smaller spread. So what you see as size depends on how wide the angle is between those lines reaching the object. A larger angle makes something appear larger. A smaller angle makes it appear smaller. And if two things take up the same angle, they appear equal in size. 5. The things seen within the higher visual range appear higher, while those within the lower range appear lower. Think of your field of vision as having a top and a bottom, like looking up toward the sky or down toward the ground. Objects that lie along the upper part of that spread of lines appear higher to you. Those that fall along the lower part appear lower. So, where something appears vertically depends on which part of your vision reaches it. Higher lines make it seem higher, and lower lines make it seem lower. 6. What is seen within the visual range on the right appear on the right, while those within that on the left appear on the left. Now think of your vision spreading out not just up and down, but also to the sides. Objects that fall along the lines extending to your right appear on your right. Those along the lines to your left appear on your left. So the position of things, left or right, depends on which direction the lines from your eye reach them. Number 7. But the things seen within several angles appear to be more clear. Imagine looking at something not with just a single glance, but with many lines from your eye reaching it from slightly different directions. When more of these lines fall on the same object, spreading across it from multiple angles, it becomes easier to make out its shape and detail. So the more angles through which something is seen, the clearer it appears. Proposition 1. Nothing that is seen at once in its entirety. Imagine looking at something long, like a stick or a line placed in front of you. From your eye, lines spread out toward it, but they don't form a continuous sheet. They are separate, diverging lines, each reaching a different part of the object. Because of this, there are always small gaps, places on the object that no line touches at that exact moment. So strictly speaking, you are not seeing the whole thing all at once, but it doesn't feel that way. Your eye shifts so quickly, sending new lines across those gaps, that the whole object appears complete, as if it were seen in a single instant. Proposition 2. Objects located nearby are seen more clearly than objects of equal size located at a distance. Imagine two objects of the same size placed in front of you, one closer, one farther away. From your eye, lines spread out toward both, but the nearer object is reached by more of these lines, while the farther one is reached by fewer. This isn't arbitrary. If the same number of lines reached both, the farther object would have to be larger to account for the greater distance, which it is not. So the nearer object is covered more fully by the lines from your eye, while the farther one is touched more sparsely. And because objects seen by more of these lines appear clearer, the nearer object is seen more distinctly than the one farther away. Proposition 3. Every object seen has a certain limit of distance, and when this is reached, it is seen no longer. Imagine again your eye sending out lines into the distance. Close objects are easily reached by these lines, but as they travel farther, they spread out more and more, leaving wider gaps between them. Now place an object farther and farther away. At some point, it slips into one of those gaps. No line from your eye reaches it. And once that happens, it is no longer seen. So every object has a certain distance beyond which it disappears, not because it is gone, but because your vision no longer reaches it. Proposition 4. Of equal spaces located upon the same straight line, those seen from a greater distance appear shorter. Imagine a straight path divided into equal parts, like 3 equal segments laid out one after another. Now step back and look at them from a distance. Even though the segments are equal, they don't appear that way. The one closest to you seems longer, the next a bit shorter, and the farthest shorter still. This happens because the lines from your eye spread out, and the farther a segment is, the smaller the angle it occupies in your vision. So even along the same straight line, equal distances appear unequal. The more distant ones seem compressed, while the nearer ones seem stretched. Proposition 5. Objects of equal size unequally distant appear unequal, and the one lying nearer to the eye always appears larger. Imagine 2 objects of the same size placed at different distances from you. Even though they are equal, the one closer to your eye spreads across a wider angle, while the one farther away fits into a smaller angle. Because of this, the nearer object appears larger, and the more distant one appears smaller. So when equal objects are placed at unequal distances, they no longer seem equal. The closer one always appears greater. Proposition 6. Parallel lines, when seen from a distance, appear not to be equally distant from each other. Imagine 2 parallel lines stretching away from you, like railway tracks. Up close, they seem evenly spaced, but as they extend into the distance, that spacing no longer appears the same. The nearer part looks wider, while the farther part seems to narrow. This happens because the lines from your eye meet those distant parts at smaller angles, making them appear closer together. So even though the lines are truly parallel, they no longer look equally distant, they seem to converge, with the far space appearing smaller than the near. Proposition 7. Objects of equal size upon the same straight line, if not placed next to each other and if unequally distant from the eye, appear unequal. Imagine two equal objects placed along the same straight path, but with a gap between them, one farther away and the other somewhere in between, not right next to each other. Even though they are the same size, the farther one can appear larger. This seems counterintuitive at first, but it comes down to how the lines from your eye spread and meet them. Because of the way these lines extend and the angles they form, the farther object can end up occupying a larger angle in your vision than the nearer one. So even on the same line and even with equal sizes, distance and position together can reverse what you expect. The farther object can appear greater than the nearer one. Proposition 8. Lines of equal length and parallel, if placed at unequal distances from the eye, are not seen in proportion to the distances. Imagine two lines of the same length placed at different distances from your eye. You might expect that the farther one would appear smaller in exact proportion to how far away it is, but that's not what happens. The lines from your eye form angles, and those angles do not shrink in perfect proportion to distance. Because of this, the nearer line can appear larger than expected, and the farther one smaller than expected, but not in a simple, predictable ratio. So even though the lines are equal and lie at different distances, what you see does not scale evenly with distance. The relation between size and distance is more subtle than that. Proposition 9. Rectangular objects, when seen from a distance, appear round. Imagine a tall rectangular object standing far away from you, like a distant building or a sign. As you move farther back, the corners become harder to see clearly. The lines from your eye spread out, and at a great distance, they no longer reach those sharp edges precisely. What remains visible are only the more central parts, while the corners fade from view. So instead of seeing clear edges and angles, the shape softens. The rectangle begins to lose its sharpness and appears rounded, almost like a circle from far away. Proposition 10. In the case of flat surfaces lying below the level of the eye, the more remote parts appear higher. Imagine standing above a flat surface, like looking down a long road or a floor that stretches away from you. Even though the surface is level, it doesn't appear that way. The parts farther away seem to rise upward, while the nearer parts seem lower. This happens because the lines from your eye reach the distant parts at a higher angle than the nearer ones. And since things seen by higher lines appear higher, the far end of a flat surface looks lifted, even though it is actually level. Proposition 11. And it is clear that things seen on a higher plane will appear to be concave. In the case of flat surfaces, located above the level of the eye, the parts farther away appear lower. Now imagine the situation reversed. This time you are below a flat surface, looking upward at it. Just as before, the lines from your eye spread out, but now the farther parts are reached by lower lines, while the nearer parts are reached by higher ones. Because of this, the distant parts appear lower, and the nearer parts appear higher. So instead of rising, the surface now seems to dip inward, as if it were curved downward, forming a concave shape, even though it is perfectly flat. Proposition 12. In the case of lines extending forward, those on the right seem to be inclined toward the left, and those on the left seem to be inclined toward the right. Imagine looking straight ahead at two long lines stretching away from you, like edges of a road or walls of a hallway. Even if those lines are perfectly straight and parallel, they don't appear that way. The lines on your right seem to tilt inward toward the left, and the lines on your left seem to tilt inward toward the right. This happens because of how the lines from your eye spread out. Points farther along each line shift across your field of vision, making the direction appear slightly angled. So instead of staying straight, both sides seem to lean inward, as if they are moving toward each other in the distance. Proposition 13. In the case of lines of equal length lying below the level of the eye, those lying farther away appear to be higher. Imagine several equal-length lines laid out on the ground in front of you, one behind the other, all below your eye level. Even though they are exactly the same size, they don't appear that way. The ones farther away seem to rise upward, while the nearer ones seem lower. This happens because the lines from your eye reach the distant lines at higher angles than the nearer ones. And since things seen by higher lines appear higher, the farther lines seem lifted, even though all of them lie flat at the same level. Proposition 14. In the case of lines of equal length lying above the level of the eye, those farther away appear lower. Now imagine those same equal length lines, but this time placed above your eye level, like beams overhead or marks on a ceiling, stretching away from you. Again, even though they are equal, they don't appear that way. The ones farther away seem lower, while the nearer ones seem higher. This happens because the lines from your eye reach the distant ones at lower angles than the nearer ones. And since things seen by lower lines appear lower, the farther lines seem to drop, even though all of them are actually at the same height. Proposition 15. In the case of objects below the level of the eye which rise one above another, as the eye approaches the objects, the taller one appears to gain height, but as the eye recedes, the shorter one appears to gain. Imagine two objects below your eye level, one taller than the other, standing one behind the other. When you stand far away, the difference between them doesn't seem as large. The shorter one appears to catch up a bit. But as you move closer, the taller one begins to stand out more clearly, and the gap between them seems to grow. This happens because the lines from your eye shift as you move. When you are closer, the taller object takes up more of your vertical view, making its extra height more noticeable. When you move farther away, that difference compresses, and the shorter object seems to gain in comparison. Proposition 16. In the case of objects of unequal size above the level of the eye which rise one above another, as the eye approaches the objects, the shorter one appears to gain height, but as the eye recedes, the taller one appears to gain. Now imagine two objects above your eye level, one taller than the other, rising one above the other. When you move closer, the shorter one seems to gain height. It appears to rise more in your view. But as you move farther away, the taller one begins to stand out more, and its extra height becomes more noticeable. This happens because the lines from your eye shift differently as you move. Up close, the shorter object spreads more across your view relative to the taller one, but at a distance, that advantage fades, and the taller object takes over in appearance. Proposition 17. In the case of objects that rise one above another, if the eye approaches the lesser one or recedes from it at a right angle, the taller one will always appear to rise above the shorter one by an equal amount. Imagine two objects, one taller than the other, rising one above the other. Now place yourself so that you move straight toward or away from the smaller one, staying along a level line, neither going up nor down. As you move, something interesting happens. The difference in height between the two does not seem to change. No matter how close or far you go, the taller object always appears higher than the shorter one by the same amount. This is because the lines from your eye continue to pass through the same point on the shorter object, keeping the comparison fixed as you move. Proposition 18. To know how great is a given elevation when the sun is shining. Imagine you want to know the height of something tall, like a tower or a tree, while the sun is shining. You don't measure the height directly. Instead, you look at its shadow. A ray of sunlight falls from the top of the object down to the ground, forming a triangle with the object and its shadow. Now place a smaller object nearby, one whose height you can measure, and look at its shadow under the same sunlight. Because both are lit by the same sun, the angles are the same, so the two triangles are similar. That means the ratio between height and shadow is the same for both. So if you know the height and shadow of the smaller object and the shadow of the taller one, you can find its height. So instead of measuring the elevation directly, you let the sunlight do the work, turning the problem into a comparison of shadows. Proposition 19. To know how great is a given elevation when the sun is not shining. Now imagine the same problem, but without sunlight. You still want to find the height of something tall, like a wall or a tower, but there is no shadow to guide you. So instead, you use a mirror. Place a mirror on the ground at some distance and stand where you can see the top of the object reflected in it. From your eye, a line goes to the mirror, and from the mirror it reflects up to the top of the object. Because reflection happens at equal angles, the path of your sight creates a pair of matching triangles, one formed by your eye and the mirror, and the other by the object and the mirror. These triangles have the same shape, so their sides are in proportion. So if you know your distance from the mirror and your height, and you can measure how far the mirror is from the object, you can find the height of the object. Even without the sun, the reflection gives you the same kind of geometric relationship, turning a difficult measurement into one you can calculate. Proposition 20. To know how great is a given depth. Now imagine you want to measure how deep something is, like a well or a pit, without going down into it. You stand at a point and let a ray of sunlight fall across the opening, reaching both the ground in front of you and the bottom of the depth. Then you extend a line along the ground and drop a perpendicular from your eye to that line, forming a second triangle. Because the sunlight creates equal angles in both cases, the triangle formed by the depth and its shadow matches the triangle formed by your eye and the ground. These two triangles have the same shape, so their sides are in proportion. So if you can measure the distances along the ground and the height of your eye, you can use that proportion to find the depth without ever having to go down into it. Proposition 21. To know how great is a given length. Now imagine you want to measure the length of something far away, like a wall or a stretch of ground, but you can't walk up to it. You stand at a point and look at both ends of the length. Then, along one of the lines from your eye, you pick a nearby point and draw a line parallel to the object you're measuring. This creates two triangles, one large, reaching the object, and one smaller, close to you. Because the lines are parallel, the triangles have the same shape, so their sides are in proportion. So if you know the smaller distance near you and how it compares to the line from your eye, you can scale it up to find the full length of the distant object. Proposition 22. If an arc of a circle is placed on the same plane as the eye, the arc appears to be a straight line. Imagine a curved arc lying flat at the same level as your eye, like part of a circle drawn on a wall directly in front of you. From your eye, lines spread out to different points along that arc. The points near the middle are reached by shorter, more direct lines, while the points toward the ends are reached by longer, more slanted ones. Because of this, the distances from your eye to different parts of the arc don't appear equal. They seem to stretch in a way that evens out the curve. As a result, the arc loses its sense of bending. Its curvature becomes harder to notice, especially from a distance, and it begins to appear like a straight line. In fact, since your eye never sees the whole arc at once, but only small parts in quick succession, those parts line up in your view, reinforcing the impression of straightness. So even though the arc is truly curved, the way your vision reaches it can make it appear flat, like a straight line laid out before you. Proposition 23. Of a sphere seen in whatever way by one eye, less than a hemisphere is always seen, and the part of the sphere that is seen itself appears as an arc. Imagine looking at a sphere with one eye, like holding a ball in front of you. You might think you see half of it, but you actually see less than a full hemisphere. From your eye, lines spread out and just graze the surface of the sphere at its edges. These outermost lines mark the boundary of what you can see. Everything beyond that curve is hidden from view. What you end up seeing is a portion of the sphere bounded by those lines, and that visible part appears as a curved edge, an arc. And because those boundary lines only touch the sphere and don't pass around it, the part you see is always less than half of the sphere. So even though the sphere is whole, your view of it is limited, a curved slice, smaller than a hemisphere, defined by the reach of your sight. Proposition 24. When the eye approaches the sphere, the part seen will be less, but will seem to be more. Imagine looking at a sphere from a distance, and then slowly moving closer to it. At first, from far away, the part you see stretches wider across the surface. But as you move closer, something unexpected happens. The actual portion of the sphere that your eye can see becomes smaller. The lines from your eye touch the sphere at points that come closer together, limiting what is visible. But at the same time, it doesn't feel smaller, because as you move closer, the sphere fills more of your vision. The angle it occupies becomes larger, making it seem like you are seeing more of it, even though the visible portion has actually decreased. So there's a quiet contrast here. As you approach the sphere, you truly see less of it, but it appears as if you are seeing more. Proposition 25. When a sphere is seen by both eyes, if the diameter of the sphere is equal to the straight line marking the distance of the eyes from each other, the whole hemisphere will be seen. Now imagine looking at a sphere with both eyes instead of one. Your two eyes are separated by a small distance, and each one sends out its own set of lines toward the sphere. If the size of the sphere is just right, so that its diameter matches the distance between your eyes, then the lines from both eyes together can reach all the way across one full half of the sphere. In that case, the limits of vision from each eye combine, covering the entire front half. So instead of seeing less than a hemisphere, as with one eye, both eyes together allow you to take in the whole hemisphere. So the amount of the sphere you see depends not just on distance, but also on how your two eyes work together, spreading their lines wide enough to cover an entire half. Proposition 26. If the distance between the eyes is greater than the diameter of the sphere, more than the hemisphere will be seen. Now imagine the same setup, but your eyes are farther apart, so the distance between them is greater than the diameter of the sphere. In this case, the lines from each eye spread out more widely before they meet the sphere. Instead of just touching the edges of a half, they reach farther around its sides. Because of this, the region seen by both eyes extends beyond a single hemisphere. The boundary of what is visible wraps slightly around the sphere, allowing you to see more than just half of it. So as the distance between the eyes increases, the visible portion of the sphere grows, until it extends beyond a hemisphere, revealing more of the surface at once. Proposition 27. If the distance between the eyes is less than the diameter of the sphere, less than a hemisphere will be seen. Now imagine the opposite case. Your eyes are closer together than the diameter of the sphere. Here, the lines from each eye do not spread wide enough to reach as far around the sphere. Instead, they meet the surface sooner, limiting how much of it can be seen. Because of this, the visible portion is smaller than a hemisphere. The boundary formed by the lines from your eyes cuts off less than half of the sphere, keeping more of it hidden from view. So when the eyes are closer together, the reach of vision is reduced, and the sphere reveals less than half of itself. Proposition 28. If a cylinder in whatever way is seen by one eye, less than half a cylinder will be seen. Imagine looking at a cylinder with one eye, like a can placed in front of you. From your eye, lines spread outward and just graze the surface of the cylinder at certain points. These outermost lines mark the limit of what you can see. They don't wrap all the way around. They only touch the cylinder at the edges of your view. Because of this, the part of the circular base you can see is less than a semicircle. And since the sides of the cylinder rise straight up from that base, the visible portion of the whole cylinder is also less than half. So even though the cylinder continues all the way around, your vision only captures a smaller part, bounded by where those lines from your eye can just reach. Proposition 29. When the eye is moved nearer the cylinder, the part of the cylinder reached by the rays is less, but a greater part will appear to be visible. Imagine looking at a cylinder from a distance, and then slowly moving closer to it. From far away, the lines from your eye touch a wider portion of the surface, so the actual part you see is larger. But as you move closer, those lines meet the cylinder sooner, so the portion they reach becomes smaller. Yet it doesn't feel smaller. As you approach, the cylinder fills more of your vision. The angle it takes up becomes larger. So even though the part you truly see is less, it appears as if you are seeing more. So just like with the sphere, there's a contrast. Moving closer reduces what is actually seen, but increases how much it seems to fill your view. Proposition 30. If a cone having a circle as its base, and the axis at right angles to the base is seen by one eye, less than half the cone will be seen. Imagine looking at a cone, like an ice cream cone, straight on with one eye. From your eye, lines spread outward and just touch the circular base at its edges. These outermost lines mark the limit of what you can see, and they only reach a portion of the base, less than half of the circle. Now, from those edge points, the sides of the cone rise up to the tip, so the part of the cone you see is bounded by those lines and that arc of the base. Since the base portion is less than a semicircle, the part of the cone built on it is also less than half the cone. So with one eye, you always see less than half of it. Proposition 31. If the eye is brought nearer on the same plane on which is the base of the cone, the part included within the vision will be less, but a larger part will seem to be visible. Imagine looking at a cone from a distance, and then slowly moving closer to it, staying in the same plane as its base. At first, the lines from your eye reach a wider portion of the cone, so the part actually included in your vision is larger. But as you move closer, those lines meet the cone sooner, and the portion they enclose becomes smaller. Yet it doesn't appear smaller. As you approach, the cone spreads across a larger angle in your vision, making it seem as though more of it is visible. So even though the part truly seen is less, it appears greater. So just like with the sphere and the cylinder, moving closer reduces what is actually included within vision, while increasing how much it seems to fill your view. Proposition 32. If rays fall from the eye upon the base of the cone, and if from the rays that fall and touch the cone straight lines are drawn from the points of contact over the surface of the cone to the apex of it, and if planes are produced through the lines that have been drawn and that fall from the eye upon the base of the cone, and if the eye is placed upon their point of contact, that is, upon the common section of the planes, the part of the cone that is seen will be quite the same, if the eye remains upon a plane parallel to the original plane. Imagine looking at a cone, and from your eye, two lines just touch its surface, marking the edges of what you can see. From those touching points, draw lines along the surface up to the tip of the cone. Now imagine planes passing through these lines, forming a kind of boundary in space. If you now move your eye along the line where those planes meet, without stepping out of that boundary, something interesting happens. Even though your position changes, the part of the cone you see does not. The lines from your eye still reach the same edges of the cone, and the angles they form remain the same. So the visible portion stays unchanged, as long as your eye moves within that same aligned path. So here it's not just where you are, but how you move. Stay within that shared direction, and the view remains constant. Proposition 33. Again, if the eye is shifted from a low position, when it is raised, the part of the cone that is seen will be greater, but will seem to be less. But on the other hand, if the eye is lowered, the part seen will be less, but will seem to be greater. Imagine looking at a cone and then slowly changing your height, either raising your eye or lowering it. When you raise your eye, the lines from your vision spread out in a way that reaches a larger portion of the cone. So the part you actually see increases. But at the same time, that larger portion is seen under a smaller angle, so it appears reduced. On the other hand, when you lower your eye, the lines meet the cone sooner, and the portion included becomes smaller. But now that smaller part is seen under a larger angle, so it appears greater. So there's a reversal here. Raising your eye lets you truly see more, but it seems less. Lowering your eye lets you see less, but it seems more. Proposition 34. If a straight line is erected from the center of a circle, at right angles to the plane of the circle, and the eye is placed upon this, all the diameters crossing upon the plane of the circle will appear equal. And if the line drawn from the center is not at right angles to the plane, but is equal to the line from the center, which is the radius of the circle, all the diameters will appear equal. Imagine a circle lying flat, and from its center a line rising upward. Place your eye somewhere along that line, directly above the center. From this position, when you look down, every diameter of the circle spreads out evenly from the center. The lines from your eye to their endpoints form equal angles, so all the diameters appear equal. Now shift the situation slightly. Suppose your eye is no longer directly above at a right angle, but still placed at a distance equal to the radius of the circle. Even then, the geometry balances out. The lines from your eye to the ends of each diameter still form equal angles. So again, all diameters appear equal. Even more generally, as long as your eye is positioned so that it sees the endpoints of certain diameters under equal angles, those diameters will appear equal. So what matters is not just position, but symmetry in how the eye connects to the circle. Equal angles lead to equal appearance. Proposition 35. But if the line falling from the eye to the center of the circle is not at right angles to the plane of the circle, nor equal to the radius, and does not enclose equal angles, the diameters with which it makes unequal angles will appear unequal. Now imagine a circle, and your eye is placed somewhere off-center, not directly above, not at a distance equal to the radius, and not positioned so that everything is balanced. From your eye, lines go out to the ends of different diameters, but this time they do not form equal angles. Because of that, the diameters no longer appear equal. Some diameters are seen under larger angles, and others under smaller ones. The one seen under the larger angle appears longer, while the one under the smaller angle appears shorter. So here the symmetry breaks. When your eye is not aligned in a balanced way, equal lines no longer look equal. Their appearance depends entirely on the angles under which they are seen, and those angles now differ. Proposition 36. The wheels of the chariots appear sometimes circular, sometimes distorted. Imagine looking at a chariot wheel from different positions. When your eye is placed in a balanced position, directly in line with the center or at the right distance, the diameters of the wheel appear equal, and the wheel looks circular. But when your eye is off-center or tilted in relation to the wheel, the diameters no longer appear equal. One direction may look longer, another shorter, and the circle begins to look stretched or distorted. So the wheel itself has not changed. What changes is the angle from which it is seen, and that is enough to make a true circle appear uneven. Proposition 37. There is a place where, if the eye remains in the same position, while the thing seen is moved, the thing seen always appears of the same size. Imagine your eye staying fixed in one place while an object moves around it. There is a certain path where the object can move and still appear the same size. As long as its endpoints are seen under the same angle, its apparent size does not change. So the object may shift position, but if it remains on that right path, like moving along an arc around the eye, it keeps the same visual size. Proposition 38. There is a place where, if the position of the eye is changed, while the thing seen remains in the same place, the thing seen always appears of the same size. Imagine an object staying in one place while you move your eye around it. There is a certain path you can follow where, even though your position changes, the object appears exactly the same size. As long as your eye stays on that path, the lines from your eye to the ends of the object form the same angle. So even though you are moving, the angle does not change, and because of that, the object keeps the same apparent size. Proposition 39. If some object is perpendicular to the plane lying below, and if the eye is placed upon some point of the plane, and if the thing seen is shifted upon the circumference of a circle which has the eye as a center, the thing seen will always appear of the same size when it is moved to a position parallel to its original position. Imagine an upright object, like a pole, standing on a flat surface, and your eye placed somewhere on that same surface. Now picture a circle drawn around your eye, and the object is moved along that circle, always staying upright and parallel to its original position. Even though the object changes its location, something remains the same. The lines from your eye to the top and bottom of the object always form the same angle because every point on that circle is equally distant from your eye. So as the object moves along that path, it always appears the same size. The position changes, but the angle does not, and that keeps its appearance constant. Proposition 40. But if the thing seen is not at right angles to the plane lying below, and being equal to the radius, is moved upon the circumference of the circle, it will appear sometimes equal to itself, sometimes unequal, if it is shifted to a position parallel to its original position. Now imagine an object that is not standing straight up, but is tilted, leaning at some angle, and its length is equal to the radius of a circle centered at your eye. Now move this object around you, keeping its length the same and always parallel to its original direction. You might expect it to always look the same, but it doesn't. As it moves along the circle, the angle under which you see it changes. At one position, it appears smallest. As it moves away from that point, it begins to appear larger. At another position, it appears largest. And in between, there are positions where it appears equal to itself again. So unlike the upright case, where everything stayed balanced, here the tilt breaks that symmetry. The same object, unchanged in size, can appear smaller, larger, or equal, depending entirely on where it is placed around your eye. Proposition 41. But if the thing seen is at right angles to the plane lying below, and the eye moves upon the circumference of a circle, which has as its center the point at which the object meets the plane, the thing seen will always appear of the same size. Imagine an upright object, like a pole, standing straight up from the ground. Now instead of moving the object, you move your eye around it, walking along a circle whose center is the point where the object meets the ground. As you move, your position changes, but something important stays the same. The lines from your eye to the top and bottom of the object always meet it at the same kind of angle. Because of this, the angle under which you see the object does not change. And since objects seen under equal angles appear equal, the object keeps the same apparent size no matter where you stand along that circle. So here, even though you are moving, the view remains steady. The object appears unchanged because your relation to it stays geometrically balanced. Proposition 42. If the thing seen remains in its original position, and the eye moves in a straight line that is oblique to the object seen, the object appears sometimes of the same size, sometimes of different size. Imagine an object fixed in place, and your eye moving along a straight path that is not directly toward or away from it, but at an angle. As you move, the angle under which you see the object keeps changing. At some positions, the angle matches what it was before, and the object appears the same size. But at other positions, the angle becomes larger or smaller, and the object appears bigger or smaller. There is even a particular position where the object appears largest. As you move closer to that point along the line, the object seems to grow, and as you move away from it, it seems to shrink. And there are also positions where the angle repeats, so the object appears equal again. So along this slanted path, the appearance does not change steadily, it shifts. The same object can look larger, smaller, or unchanged, depending entirely on where your eye is placed along that line. Proposition 43. And the same thing will happen, even if the straight line is parallel with the object seen. Now imagine the object stays fixed, and your eye moves, not toward or away from it, but along a straight line parallel to it. Even though the direction of movement is different, the result is similar. As you shift your position, the angle under which you see the object changes. From one position, the object is seen under a larger angle and appears bigger. From another, the angle is smaller and it appears smaller. And there are also positions where the angles match, so the object appears the same size again. So even when moving parallel to the object, the appearance does not stay constant. The size you see depends on the angle from your eye, and that angle shifts as you move. Proposition 44. There are places where, if the eye is moved to them, objects that are of equal size and close to one another appear sometimes of the same size, sometimes of different sizes. Imagine two objects of equal size placed close to each other. Now, depending on where you stand, they don't always look equal. There are certain positions, like along a particular straight line, where both objects are seen under the same angle, and so they appear equal. But as soon as you move away from that line, the angles change. One object begins to take up a larger angle in your vision than the other, even though they are the same size. So there are specific places where equal things look equal, but outside those places that balance breaks. The same two objects can appear unequal, simply because of where your eye is placed. Proposition 45. There is a certain place from which objects of unequal size appear equal. Imagine two objects of different sizes placed near each other, one clearly larger than the other. You might expect that no matter where you stand, the larger one will always look bigger. But there is a certain position where this is not true. At that point, the lines from your eye to the ends of both objects form equal angles. And since objects seen under equal angles appear equal, the larger and the smaller object look the same. So even though one is truly greater than the other, there exists a place where that difference disappears, where unequal things appear equal, simply because of how they are seen. Proposition 46. There are places to which the eye may be moved, and objects of equal size that are perpendicular to the plane below appear sometimes of equal size, sometimes of unequal size. Imagine two equal objects standing upright on the ground, like two poles of the same height. There is a certain line you can stand on where both of them appear equal. From that position, the lines from your eye to each object balance out, forming equal angles, so they look the same. But if you move away from that position, the balance breaks. One object begins to take up a larger angle in your vision than the other, even though they are still equal in size. So even with equal, upright objects, there are positions where they appear equal, and others where one seems larger than the other, simply because of where you stand. Proposition 47. There are certain places where the eye may be located, and objects of unequal size placed in contact will together appear equal to each of the unequal objects. Imagine two objects of different sizes placed right next to each other, touching. You would expect their combined length to clearly look larger than either one alone. But there are certain positions where this intuition fails. From specific points, the lines from your eye to the ends of the combined object form the same angle as the lines to just one of the smaller parts. Because of this, the whole can appear no larger than one of its parts. So in these special positions, something unusual happens. Two unequal objects, when joined together, can appear equal to each of them individually, simply because of how the eye meets them. Proposition 48. To find places from which an object of equal size appears half or a quarter as large, or in general appears of a size proportionate to the cutting of the angle. Imagine an object placed in front of you, and you want it to appear smaller, not by changing the object, but by changing where you stand. The size you see depends on the angle it takes up in your vision. If that angle becomes half as large, the object appears half as big. If the angle becomes a quarter, the object appears a quarter as big. So the problem becomes one of finding the right place to stand. There are positions where the lines from your eye to the ends of the object form exactly half the original angle, or any fraction of it. From those positions, the object appears reduced in the same proportion. So by controlling the angle, you control the appearance. The object stays the same, but its size as you see it can be divided just like the angle through which you look at it. Proposition 49. If an object is seen, I say that there are places where the eye may be located, and the same thing appears sometimes half the size, sometimes the whole size, sometimes quarter size, and in general in the given proportion. Imagine a single object in front of you, and instead of changing the object, you move yourself around it. There are certain places you can stand where the object appears its full size, and other places where it appears smaller, half as large, a quarter as large, or in any proportion. This happens because the size you see depends on the angle the object makes at your eye. From one position, that angle is large, so the object appears large. From another, the angle is smaller, half or a quarter, and the object appears reduced in the same proportion. So by choosing where you stand, you can control how large the object appears. The object does not change, but the angle does, and with it, the size you see. Proposition 50. If objects move at equal speed and have their ends on the same side of a straight line which is at right angles to their course, as they advance toward a line drawn through the point where the eye is located, which is parallel to the straight line before mentioned, the one farther away from the eye will seem to be ahead of the nearer one. But when they have passed the direct line of vision, the one that was in the lead will seem to follow, and the one that followed will seem to be in the lead. Imagine several objects moving side by side at the same speed, all heading in the same direction. At first, as they approach your line of sight, something strange happens. The one that is actually farther away can appear to be ahead, while the nearer one seems to lag behind. This is because the lines from your eye to those objects spread out differently, making their positions shift slightly in your view. Then, as they pass directly in front of you and move beyond that central line, the effect reverses. The one that seemed ahead now appears to fall behind, and the one that seemed behind appears to move ahead. So even though all the objects move evenly and steadily, their order appears to change, simply because of how your eye tracks their motion across its field of view. Proposition 51. If, when several objects move at unequal speed, the eye also moves in the same direction, some objects moving with the same speed as the eye will seem to stand still. Others, moving more slowly, will seem to move in the opposite direction, and others, moving more quickly, will seem to move ahead. Imagine you are moving forward, and at the same time, you see other objects moving in that same direction, but not all at the same speed. One of them moves exactly as fast as you do. Because your motion matches it perfectly, it seems to stand still, as if fixed in place beside you. Another object moves more slowly than you. As you pass it, it seems to drift backward, even though it is still moving forward, just not as quickly as you are. And a third moves faster than you. It pulls ahead, increasing its distance, and so it clearly appears to move forward. So what you see is not just how fast something moves, but how its motion compares to yours. Matching speed makes it seem still, slower makes it seem to fall back, and faster makes it seem to move ahead. Proposition 52. If, when certain objects are moved, one is obviously not moved, the object that is not moved will seem to move backward. Imagine some objects moving in front of you, while one object remains completely still. Even though that object does not move at all, it doesn't appear that way. As the other objects shift position, coming closer or moving farther, the still object seems to slide in the opposite direction. So the unmoving object appears to move backward, not because it changes position, but because everything else around it does. What you see is not just motion itself, but motion in relation to other things, and that can make stillness look like movement. Proposition 53. When the eye moves nearer the object seen, the object will seem to grow larger. Imagine looking at an object from a distance, and then slowly moving closer to it. At first, the lines from your eye to the object form a narrow angle, so it appears smaller. But as you move nearer, those lines spread out more to cover it, forming a wider angle. Because of that, the object seems to grow in size. So the object itself does not change, but the angle through which you see it does, and that is what makes it appear larger as you approach. Proposition 54. When objects move at equal speed, those more remote seem to move more slowly. Imagine two objects moving side by side at the same speed, one closer to you and one farther away. Even though they cover the same distance in the same time, they don't appear to move the same way. The nearer one seems to move faster, while the more distant one seems to move more slowly. This happens because the farther object is seen under a smaller angle as it moves. It takes up less change in your field of vision over time, so its motion appears more gradual. So even with equal speeds, distance changes how motion is seen. The farther something is, the slower it seems to move. Proposition 55. If the eye remains at rest while the things seen are moved, the more remote of the things seen will seem to be left behind. Imagine two objects moving in front of you, one closer and one farther away, while your eye stays still. Even though both are moving, they don't appear to move the same way. The nearer one seems to pass through your field of vision more quickly, while the farther one changes position more slowly. Because of this, the more distant object appears to lag behind. It seems as though it is being left back, even though it is moving just like the nearer one. So once again, distance changes appearance. The farther something is, the more slowly it seems to move, and the more it appears to fall behind. Proposition 56. Objects increased in size will seem to approach the eye. Imagine looking at an object, and suddenly it appears larger than it was before. Even if it hasn't actually moved, your mind connects size with distance. Things that are closer to your eye usually appear larger, and things farther away appear smaller. So when the object seems to grow in size, it also seems to come closer to you. The change in size creates the impression of motion. The object feels as if it is approaching, simply because it now fills more of your view. Proposition 57. When things lie at the same distance, and the edges are not in line with the middle, it makes the whole figure sometimes concave, sometimes convex. Imagine 3 points forming a shape, 2 at the sides and 1 in the middle, all at the same distance from you. If the middle point lines up in a certain way, the shape may appear to curve inward like a shallow bowl. But if that middle point shifts slightly, coming closer to your eye, the shape begins to curve outward instead. So even though the outer points stay fixed, A small change in the middle can change how the whole figure appears. It can look concave or convex, not because the shape itself changes, but because of how its parts are arranged in your view. Proposition 58. If from the meeting point of the diameters of a square a perpendicular is drawn, and the eye rests upon this, the sides of the square will appear equal, and the diameters also will appear equal. Imagine a square lying flat, and from the point where its diagonals meet, a line rises straight upward. Now place your eye somewhere along that line, directly above the center. From this position, the lines from your eye to the corners of the square are balanced. They form equal angles, and because of that, all the sides appear equal, and even the diagonals, though longer in reality, also appear equal. So the whole figure looks perfectly regular from this point. But if your eye shifts away from that balanced position, no longer directly above, or not aligned equally with the corners, then that symmetry breaks. The diagonals no longer appear equal, just as in the case of the circle, and the figure begins to look distorted. Our audiobook ends here. Thank you for listening. If you want any particular book in this channel, please let us know in the comments.